set for the two classes that we missed last week. So I would request the class representatives, if they are present here, so to discuss with your class, and then let me know what is the convenient time. So we can have it one, two this week and another next week, and we can have it tomorrow if it is possible, or on a Sunday also. It is fine for me. So either tomorrow, or since Thursday and Friday we will have regular class, so we can have it either on then Saturday or Sunday. So similarly, another extra one we will compensate in the next week. Okay, so I request all the class representatives. Anyone present? Any class representatives?
Yes, sir.
Yes.
Yes, sir.
Oh, yeah. So you discuss with your class and let me know the time. Okay.
Okay, sir.
Because you must be having other classes, so I don't want to uh, uh, make confusions. So you decide the time, so we can have in the morning like this time, or in the afternoon or evening. Everything is fine for me. Okay.
Sir, we have to look for 1 hour slot in this week.
1 hour slot, yes. So 1 hour
Okay,
slot
sir.
this week and 1 hour slot next week.
Okay, sir. Thank you.
Okay. Okay, so let me share the screen here. Okay, so the topics we will be covering, like so mostly we will be looking at the fundamental aspects of optics, so interference and probably some applications of that, and then diffraction, so which are the classic optic optical phenomena that, yes. Any question? Okay, so if not, so best is you keep your microphones in mute mode. Uh, and if you want to speak something, you can raise your hand or put your questions in the chat box as well. So that is also fine. Okay. So basically the topics will be the interference, diffraction, and then we will discuss about polarization, and if there is time, so we will also talk about the microscopy. So basically I will be following the course content that has already been shared with you, and depending on the time and how much time we have, so we will see how much we cover. So I don't want to go too fast, so that you don't understand anything. So if you find or don't understand something in the class, you can contact me later, or in the next class also. So I will always start with question answer, like, or I would like to hear questions from you whenever we start the class. So if you have any doubts or anything, so you can ask in the beginning of the class as well. The book, again, we will be following this book, Ajay Ghatak's book, which is already mentioned in the course content that has been shared. So this is the 6th edition. So I'll be following this book only. And there are also other reference books which you can also follow. But mostly I will be sticking to this book. And I request that all of you should download this book, a PDF copy of this book, and go through the chapters which I'll be teaching in the class. Uh, so, and the evaluation, so I am planning to have 2 quizzes. So one I will probably take this week, so either on Saturday or Sunday, and the next one I will have again the next week, and then there will be one assignment. and of course there will be the end sem evaluation in first week of March. Okay. So this is the post. I mean, this is what we will be, I hope to cover during this couple of weeks, or this week and next week. Okay. So, any questions so far?
No, sir.
No. Okay. Okay. So let's start with then. So when we say optics, so what is optics? Optics is basically study of light. So this is the light which is in the visible range, so that you see here, so that you can see the visible range. But that is basically what the study of propagation and interaction of light with different material, different medium. So how light propagates through different materials. So this is what the optics is all about. And mostly optics in a classical sense is always concerned with the visible range. But as you know, your electromagnetic wave starts from radio wave to up to X-rays and gamma rays. So optics, each electromagnetic wave will have their own uh, understanding of optics and so on. But the concepts that we will be studying during this course, so those are applicable to all kinds of waves actually. So it is not only applicable to the visible range, which normally you see or you perform in the lab using lenses, but it is applicable to all kinds of waves, including electromagnetic waves. And light, this is the visible light, is basically it's a part of your electromagnetic wave. So what we are going to study then is study propagation and interaction of electromagnetic wave So this interaction of electromagnetic wave, the interaction can be with itself, okay, or it can be with other materials or other mediums. Okay. So if you look at the application of optics, so there are like many applications. So I will point out few applications which you might be, some of you will use it extensively when you go deeper into your core subjects. Okay.
Excuse
So
me, sir.
yes.
Sir, what is interaction here?
Oh, interaction. Interaction means so let's say how do you, when you meet someone, okay, some person or somebody, so what is it called? So you introduce yourself and then talk about, you ask who the other guy is, what do they do. So it is like what you have is known as interaction. Okay. So similarly, electromagnetic wave, so when you have one source or one so which produces certain kind of electromagnetic wave, so when they are propagating, so they can then meet maybe another wave, they can meet another medium. So if it is going from air to glass, let's say, okay, so this process is known as the interaction. Okay. So basically, how a wave or what happens when one wave meets another wave or another material or another medium. So this is basically what we call as interaction in physics. Okay. So is it clear or?
Okay, sir. Clear.
So this is a very general or generic term, this interaction that is normally used in physics or in science as well. So even let's say when we say, so not only waves they interact, it is also, for example, electrons. When a charge particle, so we also say, so you already learned about the charge particle, stationary charge, the charge when it moves, there is a current. So all the charges when you have, so they are also, they can also interact. How do they interact? So they interact due to this Coulomb interaction, correct? So when a charged particle, positive or negatively charged particle, encounters another charged particle, so there will be a interaction which is known as Coulomb interaction. Okay, so the force, they will experience some force, there will be some electric field. Okay, so similarly, this electromagnetic wave, which is nothing but your oscillation of electric and magnetic field. So when they are propagating, so this electric field and magnetic field, they will also interact. And this is what I meant by this interaction. Okay, so the applications of optics is actually there are the applications are like pervades all fields. Okay, all fields of science and engineering. So a couple of examples I will give. So the most the famous I think application you know about your microscopes, optical microscope. So where basically what you can do is you can see small things or tiny things which are not visible to your eye, so you can magnify things, okay, or small objects using some tricks, some lenses, and this propagation of light. So magnifying, to magnify little or small objects. This is a very useful application of optics. So there are various kinds of microscopes. So if we have time, we will look at some of the applications in microscope. So another example is again your telescope, so which you already, so some I think aspects of microscope and telescope you already have learned in your 12th. So this is again, you can look at objects which are far away from you. So for example, you can look at stars, planets. Okay, so this is your telescope, which uses they use a lot of optical components, and basically it is based on how your electromagnetic wave interacts with your lenses. So then the third one is known as spectroscopy. So spectroscopy is a technique. So you will so since you don't have the lab courses this semester, so hopefully next semester you will have lab courses in physics. So in that course, so you will also see how the spectroscopy, you can perform some spectroscopy related experiment related to optics. Basically what you can do is you can identify elements or electronic states. Okay, basically you are looking at a spectrum of your or you can spread or differentiate a spectrum of your electromagnetic wave to study their study different materials. So in a way we can say, in a general way we can say that you can identify electronic states or chemical states of material. So that means which kind of element that is present in a material and what is the electronic configuration. So these things you can actually understand using the spectroscopic techniques. Then if you look at a more useful application, the engineering application. So you have the this telecommunication, that is again a part of optics, right? So you have your mobile phones, so how you communicate, then how the data is transferred, so the optical fibers. So these are all come into your 5G, 4G, 5G communication. So this comes under this telecommunication, which is nothing but the propagation of electromagnetic wave and which carry the information. Okay? So this is your telecommunication. So this is again a very different field of application of optics. Another one is more related to devices which are known as optoelectronic devices. So where you can use electricity or current to generate light, okay, or you can also do the vice versa. So you can also use light to generate electricity. So these are basically a combination of your electronic devices, like you know about transistors and diodes and so on, which actually you combine with optical materials which help in running these devices. So example will be your, so a light emitting diode, so LED. So which basically, so if you do a course in future in electronic material or in electronics, so you will know more about this optoelectronic devices, but we will not discuss this in this course. So light emitting diode is basically, it's a diode when you are biasing it, so you can get light out of it, which you use normally for display. Okay, so your displays, many of the displays that are used nowadays are basically LED displays. Then you also have solar cells. Okay, so where you can use the light, sunlight, or the photons. So the photons are nothing but the quantized form of your electromagnetic wave. So these solar cells basically use these photons and convert that energy to useful electrical energy, which you can store and then use it for other applications. Then another very interesting field is of laser. So laser you must have seen and used already, and this laser is again another complete different field of application of optics. And this laser invention of laser actually has kind of made possible many of the modern uh, engineering applications. In, you can use laser in as a mechanical engineer, as a in biology, for biomedical engineering. So you can perform a lot of make many devices, biomedical devices based on this laser. uh, and you can do, like, you can cut, you can polish things, you can deposit many materials using laser. So laser has really many different applications, so which comes from this optics field. Okay, so you can do many precise measurements. In fact, a laser combined with the optical phenomenon of interference is used as a standard for defining your distance. So you can define distance like 1 meter. So how you can define? You can define really precisely using laser and interferometers. So where interference is the optical phenomena that works. Okay. So before you can go into all these detailed applications, the best is to understand some of the fundamental physics that are involved in these applications. So we will look at these fundamental aspects. And so let's say when light is propagating uh, through air now, and it encounters a material. So I have a material, okay, and I have a light wave which is propagating like this and meets this medium, okay. So what can happen in that case? So one thing, the light can get reflected, okay. So it can be reflected, it can be transmitted, just go through like this. It can be transmitted, it can get refracted, right? So this you all know. And some light can also get absorbed, so or it will get attenuated within the material, so this wave may not go pass through the whole medium, so it will be absorbed within the medium. So many things can happen when light is propagating through a medium. And to understand all these different aspects, so optics has been divided into two parts actually. So optics, we can say, the one is known as geometrical optics, or sometimes it is known as a ray optics as well. And the second part is known as wave optics. So you are very familiar with the geometrical optics part, where you learned about the laws of reflection, refraction, okay. So how light propagates through or through lenses or through mirrors, okay. So this is all comes under your geometrical optics. So your geometrical optics is basically the propagation of light through mirrors or lenses, okay. So this is your geometrical optics, and here uh, you assume that your light is like a ray. So it is like a ray which travels, most likely it's a rectilinear motion of your light. So it travels in a straight line path, and by tracing the ray, so you can understand how the light propagates through these mediums. So here you don't really think about light, whether it is a wave or anything else. You just consider it as a ray, and what is most important here is the refractive index of the medium. N. So this refractive index will, if you know that, so you can then explain the reflection, refraction, and so on. But when we talk about wave optics is like where we are considering the light is as a wave, and basically you can describe the phenomenon like interference or diffraction, okay. So that means you assume your wave has some amplitude, wavelength. So these things you need to know. The velocity, okay, and the phase. Phase is another important parameter or concept in wave optics, which actually comes into picture when we talk about interference. So there's two distinct approach to understand optics. So you can explain some of the phenomena using geometrical optics and some of the phenomena using wave optics. Okay? So, but electromagnetic wave, it is not a wave also, it's like a particle also from quantum mechanics. So it behaves also like that the light that is emitted in electronic excitation and de-excitation. So this is known as a quantum of energy, which is known as photon. So your light is also behaves like a particle. So that is a photon. So therefore, sometimes you call light is neither a particle nor a wave. So it is neither nor. So it is not clear what it is. So it depends on what application you are looking at. Based on that, the light can behave as a wave or a particle. So I will ask one question, and I will put it in the Google Classroom as a question. So you can start thinking about it and post it in the Google Classroom in the meantime. So the question is, so if you look around you, so you see many optical phenomena. So now think about two examples. So one example where you think your optical or geometrical optics is able to explain the optical phenomena, so behavior which can explain by geometrical optics. And another example you think about which you need the wave nature of light, or you use wave optics to describe that phenomena. So you can think about that, and I will put that question in the Google Classroom. I'll post it now. So you think about it, and maybe towards the end you can answer it. So it is not really so there is no point here, but just to make you think about these different phenomena, optical phenomena that you have seen or you have experienced. So it is, don't take anything from the book. So you can explain some experiments or some phenomena which you have seen yourself and try to answer that. Okay.
So do we need to put the answer in the private comment?
So you can put it in the Google Classroom. So I have posted the question there. So you can put your comments and answers there later. Okay,
So
so
means we need to put the answer so that it is viewable to all or
yes,
personally
yes,
to
it's
you.
visible to all. Yes, yes, yes.
Okay, sir.
So it is like a general discussion we will have, where so so to you can think right now, and maybe later on you can also add to that if you come up with some interesting optical phenomena that you think probably uh, belongs to you, or you can explain using wave optics or geometric optics. Okay, so before going into the interference part, so briefly I will touch upon this geometrical optics thing. So the geometrical optics is purely based on the Fermat's principle. So your Fermat's principle uh, clearly is used in understanding the geometrical optics. So what is the principle? So if I have a point A and I have a point B, and I want to know what is the path taken by the light when it goes from point A to point B. So there are many possibilities. So it can go like this, it can go like this, it can go like this. So there are many paths that are available for the light ray to go from or travel from A to B. Then which path the light should take? So that is basically we're asking the question. So the ray. So here when we are saying ray, that means we are saying the light ray or the optical ray. And what is the path taken by the ray from A to B? So these are all possible. So this is, let's say, a curve ACB. It can follow this path. It can follow AC prime B. It can follow AC double prime B. But according to Fermat's principle, so the path taken by the ray is the one for which the time taken, the tau, the time taken to travel from A to B is an extremum. So it can be a minimum or maximum or a stationary. So it should be a extremum. So the time tau taken from A to B is an extremum. So you can do a little bit of, so when you, let's look at the time taken by the ray when it travels along ACB. So what is the time taken? So that we can calculate by taking a small section in this ACB, this curve. So let's say we are saying that ray traces this curve ACB. So if we say this is a small cross section here, DSI, and it has a refractive index N. So what is the time taken to go from or cover this distance DSI? So this is nothing but DSI divided by your velocity of light by N. So C is your velocity of light, speed of light, okay? And N is your refractive index. So this time, this is equal to N dSI by C. And what is this N dSI? So this N dSI is known as the optical path. So this is the length of the optical path or optical path length. So it is different from your normal path length. So it is the path length covered by the light. So N dSI. And to know the calculate the total time, so we will just sum over all this time, tau I, which is nothing but summation over I N. So maybe this N can also vary from point to point. So in that case, rather we should say it is Ni dSi. So it is Ni dSi by C. And which for a continuous curve like this, so we can write it as a integration in this form, N ds from A to B to C. So now if we can calculate the tau from A to B over all these possible curves and compare, so whichever is the minimum or extremum, so that will be the path taken by your light. And in a way, so this Fermat's principle basically tells you what is the direction of light or the ray should go or travel along when it travels from point A to B. And this is put in a different way actually. Yes, question. Yes. Is it like
So
question?
why
Yes.
tau is an extremum is written?
Yes, it is extremum because so normally you probably might have seen it is always minimum. It is you the but extremum means it can also be you can consider it as minimum or stationary. So stationary means there is no change when you change the curve. Okay, so you cannot say that light will travel always when the path taken is the minimum time. So if it is, let's say, uh, if the time taken from A to B via curve C and C double prime is the same, okay, so there is no change in the time, so both paths are possible. Okay, so in that case we say there is no this tau is it's stationary, it is not changing. Okay, so it is, there is no minimum or maximum here, so that means all paths are possible. So to make it complete this principle, so this extremum word is used. But generally when we talk about it, so we say so we represent this principle in a slightly different way. What we say is mathematically that we say this integral n ds or the change in the path. So if you change the path by delta, a small amount, this change should be your the optical path length, the change should be 0 when we go from A to B. So if that is the case, so that means if I have a point A and point B, and I say this is my path, and now I modify this path a little bit by some amount delta, okay, and now I can find a difference between this n ds A to B over C minus n ds A to B over C prime. So if it is 0, so this is what this statement means, delta n ds is equal to 0. So that means there is no change in the path length when you change the actual path a little bit. So this is like a stationary path. The basically you see it's a stationary path, and this is what the light ray would take this path. Okay, or in a way you say the actual path of the ray is between 2 points is the one for which the optical path length, the optical path length is nds, is stationary. Okay, so there is no change in the optical path length. So that is the one which will which your light will take that path. And when we see in a and since this n is there, so if you say a it's a homogeneous medium, that means n is same everywhere. Okay, or a isotropic medium. So for isotropic medium,
Sir, can you repeat once, sir, please?
so this statement or the principle states that uh, the ray will take a path while traveling between a point A to point B. So the path will be such that if you change the optical path by a small amount, so there is no, or if you change the path by a little amount, the optical path length will remain the same. So you can change the curve A to B, so it follows the ACB path or AC prime B path. but the optical path length, that NDS, there is no change in that. So that means, let's say if I have ACB with a, so why the optical path length comes here? Because of this refractive index N. So here I can have a refractive index N, and I can have a refractive index N prime here. So
Yes,
while the ray travels through A to B to this ACB curve, so the optical path is NDS1, let's say, and the other one is N prime DS or DS, I can say this like this, and this is NDS prime, okay?
prime.
So this will be 0. So because it is possible that the optical path, the path actually changes, but the optical path is not changing.
Optical part does not change. Yes.
And this is
Thank you, sir.
because we have the refractive index there.
Yes, sir.
Okay. And if you have a homogeneous medium, so where n is not changing, so the extremum or the minimum is a straight line. So that is why we say in a homogeneous medium, when light travels, it travels in a straight line. It's a rectilinear motion. So because it's a homogeneous medium. But if it is a non-homogeneous medium where you have a variation in your refractive index, so this principle can be changed. And that's why we are saying we are using the extremum term. So this Fermat's principle you can use. I think you probably must have done it in your 12th. So where you can derive your laws of reflection. So using this Fermat's principle, so you can derive laws of reflection. That means your angle of incidence is your angle of reflection. So this is purely based on the trigonometric thing. You can calculate that. So I will not do the derivation here. So you can look it up in the book by Ghatak. So laws of refraction. This you can also derive using this Fermat's principle, where you basically write your n1 sine theta 1 equal to n2 sine theta 2. This is your result that you will get using this Fermat's principle. So some of the optical phenomena which so maybe you can also write. So I will give you an example is a mirage that you observe. Some optical illusion that are created can be explained based on this Fermat's principle and laws of reflection and refraction. And mostly those phenomena are described in a non-homogeneous medium. Okay. So this is briefly a recap of the geometrical optics part. So now we will move to the wave optics. So when we say wave optics, so that means we are assuming, or we are saying that our light behaves like a wave. And to describe the wave feature of like any general wave motion, so you in one dimension we use an equation, the wave equation in one dimension. So I think you already know about this, which is given by this expression, so which is v square del square psi by del t square. So your psi is your describes your wave, and your v is your, so as a function of, so this is, that is a function of your x position and time. So this is the wave, how it propagates in general. So it can propagate as a function of a position or your space, as well as a position as a function of time. and v is your velocity of wave. So it propagates, it can, so if it is in one dimension, so it can propagate along positive x or negative x. And normally the solution would be of the form, you can write it x minus vt plus g x plus vt. So this fx minus vt represents a solution, it's a function which tells that the wave propagates in the positive x direction. This is positive x direction, and this propagation tells you it is in a negative x direction. Okay, both have the same velocity v, and will also have the same wavelength and frequency and so on. So you can look up to some examples in the book. So I will just write down those examples. So if you solve, so you will understand why I am writing the solution in this form. So look at examples 11 point or section 11.9 from the book, and examples specifically 11.5 and 11.6. So this is from the 6th edition. So that's why. So I will give some of the, or ask you to solve some of these examples. So which as a homework. So you do that so that you can understand things better. So this is your wave equation, which basically describes the propagation of wave as a function of position and time in one dimension. This is a very general wave equation, which is true for all kinds of waves. So you can talk about water wave, sound wave, okay? So all will follow this wave equation. And
Excuse me, sir.
yes,
So can you specify the book's name?
Ajay Ghatak, I mentioned in the beginning, no?
Okay.
The name
Have you got the
I will
PDF?
post it in the Google Classroom. Okay, so you have the. So I will not share the entire PDF file, so you can download it easily. I will just post the title line. So this is 6th edition. Okay, I'll put it in the Google Classroom so you can download. Anyway, I will upload this also, so you have the reference of the book name all the time. Okay, and yes, so this is your wave that you can define how a wave propagates in one dimension. In 3 dimension, this expression will change a little bit. So there you will write del square psi is equal to 1 by v square, del square psi by del t square. So this is a mathematical representation of the wave. So what we are doing is representing this propagation of wave in a mathematical formulation, then which will help us in solving problems later on. And here del square, I think this term also you must be familiar already with this term. This is del square by del x square plus del square by del y square plus del square by del z square. So this is the partial derivative with respect to x, y, and z. So the left hand side tells you how the wave propagates as a function of position, okay, or how it propagates in space, and the right hand side tells you how the wave propagates as a function of time, and v is the velocity. So in case of for electromagnetic wave, this v is nothing but your c, velocity of light. So if you are asked to write the wave equation for electromagnetic wave, so everything this you can write like this: del square psi by 1 by c square, del square psi by del t square. And the standard solution is, what is the solution of this? So if we are saying in a 3-dimension, so it is your wave as a function of r and t, which we can write like this: a exponential I k dot r minus or plus minus omega t phi. This is a complex solution. So if you substitute, so are you familiar with this complex solution,
No, sir.
or you are familiar more with the
No, sir.
cosine form? So you can also write the cosine form. Cos. So in 1 dimension, we will write it as cosine kx plus minus omega t plus phi. Okay. Or if it is 3-dimension, we will write k dot r. Okay. So you can write k dot r in 3-dimension, or you can also, this is the real part of this function that we are taking. So kx plus minus omega t plus phi in 1 dimension. So if you substitute these solutions in the wave equation, so you will see actually, so you have a solution for that wave. So that's why we are saying, so these are the solution of the wave equation, and this is how the wave propagates. So it is both as function. So a is the amplitude, and what is k? K is the nothing but 2 pi by lambda, where lambda is your wavelength. And what is omega? Omega normally is related to your frequency, k square v square, and so omega will be equal to 2 pi mu. Okay, so mu is your frequency. So this is related to your, so omega and k are basically related to your wave in terms of lambda and wavelength and frequency. So if you substitute these solutions in the wave equation, so in 3-dimension you can also try it, and also in 1 dimension also you can try it, and you will see that your left hand side and right hand side will be equal. Okay, so this is how the wave will propagate. But most interesting thing happens when this wave encounters some obstacle. That means if you have a wave which passes through a hole or a slit, okay, or like a straight block which is basically blocking it. So all these parts will create interesting optical phenomena, and we will look at it. So since it is quite a bit of time, so I will not start with that, but basically then in the next class, so we will discuss about how this wave, when it encounters different optical blocks. I mean, by that, I mean, it can be a hole or it can be a slit. Okay. So these kind of obstacles which will block the propagation of your electromagnetic wave. So you will see how that creates interference and diffraction and so on. Okay. Any question? Okay, so if not, so we'll stop for today now, and let me know the time for the extra class this week and next week. So I have posted the question in the Google Classroom, so you can have a look and try to answer, and try to think about these different phenomena, optical phenomena that you can think about so you can see around you, which can fit into those two aspects of geometrical optics or wave optics. Okay. Any question?
Sir, please can you share this PDF also?
Yes, sir.
Yes. Okay, so if not, then thank you. So we'll see you again
Thank you,
the
sir.
next time.
Thank you, sir.
Thank you, sir.
Thank you so much, sir.
Thank you, sir.
Thank
Thank
you, sir. Thank you, sir.
you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.